Okay, so continuing on with more examples, find the length of the curve or the arc length for this equation given on y being between 1 and 2. So in this case, we kind of don't have a choice. X is already isolated for us, and we're given y values to look over, so it looks like this is going to be a dy problem. So I can just go directly to finding dx dy or x prime. So again, I wouldn't want to mess that up and try to solve for y. It'll get really ugly. Just x as a function of y is perfectly fine, and I'll just deal with it in that form. So in order to find dx dy or x prime, I'm going to just rewrite that as 1/8 times y to the 4th plus 1/4 times y to the negative 2, so I can deal with it as a couple of power functions and differentiate them quickly. So 4y cubed plus, bring down the negative 2y to the negative 3. Remember, I'm differentiating here. Let's clean this up. So I got my x prime to be a half y cubed minus a half y to the negative 3. Next, I got to go square that thing. So you can apply the formula for binomials squared, or you can write two of them and go multiply it out. Your choice. I'll show all the work and multiply it out. So I got a 4th y to the 6th, and I got a negative a 4th y cubed and y to the negative 3. Add the exponents, get a 0. Same thing in the middle terms, inner terms. Negative a 4th y to the 0, and then negative a negative positive a 4th y to the negative 6, it looks like. Now let's clean it up a little bit more. So y to the 0 is 1, y to the 0 is 1, and I basically have negative a 4th and negative a 4th. Combining them gives me a negative a half. So this is my x prime squared. So it's 1 plus the derivative squared, which I have here, and I know I was going to have a dy problem because it was x isolated. And my limits of integration are from 1 to 2, and they are y values accordingly. So then let's combine like terms here. It looks like I can combine the 1 and the negative a half. So 1 minus a half is a half, plus the 1/4 y to the 6th minus the 1/4 y to the negative 6, which kind of looks ugly, and we're going to sort of cheat and recognize that this format kind of fits this format. And how did we even get to that format? We got to that format from having squared two things that were identical. So we're going to sort of retrace our steps and recognize that maybe this guy is factorable into something nice like this, and that would be nice because square root of something squared would just pop out the inside. So this guy is actually a perfect square. If I rewrite it as this, that pretty much looks like this guy. So I have 1 to 2, some binomial looking thing squared, and it must be a half y to the 3rd and a half y to the negative 3rd. And the negative was throwing me off. This should be a plus actually, because I realized that doesn't factor the way I want it to factor. So I had my x prime squared here. It was a positive 1/4. I don't know why I put a negative. That should be a positive. That should be a positive. I copied it wrong. And this should be a positive. Now that is nice because everything is positive. And if I square this, meaning if I write two of them next to each other and multiply them out, I'm going to get this. And again, it was just kind of using this idea backwards. Wait a minute, this looks like that, but that came from something squared. And you don't have to do it this way. You could take the y to the negative 6 in the denominator and get a common denominator, and you'll end up with the same type of thing where you end up with a binomial squared. So nicely, that works to our advantage. So the radical goes away, and I have a half y cubed plus a half y to the negative 3 dy, which is just some power function looking thing to deal with and integrate. So we end up with a half times y to the 4th over 4 plus a half times y to the negative 2 over negative 2 from 1 to 2, I guess. Plug in our limits of integration, and it looks like we end up with 33 over 16, or approximately 2.06-ish for the arc length of this guy. where were we? Of this guy between 1 and 2. So there was a lot of algebra and little tricks involved, but overall it wasn't that bad. This is a rational value, so maybe our calculator can give us a pretty good idea of whether we did this correctly or not by just going and looking at the integrate function. So let's go up to this point, the very first step where we use the formula, and let's punch that into our TI, or maybe the simplified version, and see if we get the 33/16 or about 2.06, just to double check our work. Let's say if this were a test or a quiz. So I'm going to do math 9, and then I'm going to put, maybe let's put this garbage under the square root as our function. So let's hope I don't make any mistakes. It's the square root of 0.5 plus 0.25 y to the 6th, or in my calculator x to the 6th, plus 0.25 x to the negative 6, comma, in terms of x, and the limits of integration are from 1 to 2. And let's see what we get. So we get, actually, it's a good check. Let me go to math and then push 1. That'll give it to me in fraction form if it's a rational number. Push enter, and voila, we got the 33/16, or the 2.06, which is what we had gotten over here. So that would be a good double check to make sure you didn't make any mistakes in the process. Now, if it is a rational number, of course, your calculator can convert it into a fraction. If the value that you get is irrational, or sometimes your calculator uses approximation methods, and the value that it gives will be close to what you got, and maybe sometimes not exactly the same. So let's also quickly define the arc length function. So far we've looked at the arc length between two fixed points, either x values or y values given. But we can also define the arc length formula as it being a function in itself, and the idea is that if I have a curve and I'm interested in the arc length from a fixed point A to some other x1, I can come up with a function that defines that length. And then maybe if I want to change my mind and go to a little bit further and get that length, that function that I develop will spit out all those different arc lengths. And that function we'll call s of x. And we still have what we developed earlier, f prime of t, and I'm using t just as a dummy variable. It could be whatever variable you wanted. So it's still 1 plus f prime squared, only now I'm going from a fixed point x to some other random x value wherever I choose to stop. So this is exactly the arc length formula we developed before, except whatever I evaluate as my integral, when I go from a to x, x is the variable term that keeps changing depending on which point I want to go and stop at to get the arc length for. So this is a function of x once I integrate and I put in my limits of integration. So whatever variable you use, t or z, it doesn't matter. This ultimate result will be a function of x. So as x changes, you get different arc lengths. So let's go use this. It's not a whole lot different than what we did before. The only thing is the 2 points are not necessarily fixed, and it's a variable point that you're stopping at. And let's go look at an example. So it says to find the arc length function for this curve, we'll call it, from the starting location, from the starting point P. So whatever this thing looks like, which we should be familiar with, it's a simple function. This is actually a linear function. And so we're going to go ahead and maybe just isolate y. We could isolate y or x. It doesn't matter. I just want to isolate y and set up a dx problem. So here's my function. I'm going to go through the same business since y is isolated and do the arc length formula. So that business is the same. This is my y as a function of x. I found my y prime, which is a simple -3/2. I squared it. Find y prime squared. That's 9/4. Use it in the formula just like we did before, 1 plus the derivative squared. And I'm choosing to set up a dx problem because I isolated y. Now my limits of integration, remember you would have from an x to another x, or from a y to another y. Since this is a dx problem, I'm going to start from an x and end at some random x because it's going to be a function of x, not a fixed value that I'm going to get, but a function of x. So I have to choose the starting point correctly, which value. Since I chose to do a dx problem and the point starts at 0, I'm going to have an x coordinate of 0, and then it's a function of x that I'm looking for, and I'm going to stop at some random value x. So the only thing to kind of watch out for, and it's different, is that my upper limit is going to be x because I chose to do a dx problem. So this will just ultimately give me a function of x that relates how the arc length function behaves starting from this point 0, 3 and keep on going to some other random value x. So again, remember I need a starting value and an ending value, and in this case a point x comma y was given to me, and I chose the x coordinate because I set up a dx problem. So this integral is going to be really quick because it's just a constant there under the radical. So not to make things confusing, because this was going to be a function of x, I know in my mind I had set up a dx problem. I'm going to go ahead and choose t as my dummy variable, so I'll have everything in terms of dt. Again, that doesn't matter what variable you choose, but since my upper limit was going to be the variable term x, I just wanted a different variable for my integrand. So then I have get a common denominator, root 13 dt. I pulled out the 1/2 from the square root of 4, put it in the front. So I have a half square root of 13t from 0 to x. Plug in your limits of integration, and it looks like we get root 13 over 2, and x minus, when I put in 0, I get 0. So let's talk about what this function describes. I ended up with a linear function that gives me all the different arc lengths for this curve, starting at 0, 3 and going off to whatever x value I want to stop at. So for example, if I say find s of 2, you're going to get root 13, it looks like. Now, what does that mean? What did we just find? We basically found the distance, or the arc length, from the starting point x equals 0 to the stopping point 2 on the curve of interest, which we isolated for y by choice. Now, if I change the x to a 5, it'll just give me the distance on that curve from 0 stopping at 5. Now, the curve we're dealing with is just a line, the simple y equals -3/2 x plus 2. So let's quickly talk about what we just found and how we could have done it using the distance formula. So this function is a function that describes the distance starting at the point 0, 0, 3, and I have to be careful because I think I graphed it wrong quickly. So again, this was the original function given, 3x plus 2y equals 6, then we chose to isolate y. I fixed that, I had the wrong y-intercept, and I graphed it, so the starting point was 0, 3, and we kept moving x over up until wherever we wanted to go to. So from here on to whatever location you want to go to get the length, and when we analyzed stopping at 2, we basically wanted to know, starting at 0, 3, going all the way to the x coordinate of 2, what was going to be that length. And since we already had the function ready to go, all we did was plug in the 2 and it gave us that distance. But this is just a linear function. We could actually find that distance by looking at the distance between the two ordered pairs and using the distance formula, and we better get the same answer. And that, we can quickly use the distance formula, x2 minus x1 squared, y2 minus y1 squared under the square root, or notice that this is just 3 units, this is just 2 units, and if I want that distance, it's just going to be 3 squared plus 2 squared, which is 9 plus 4, which is just square root of 13, which is what we got using the function we developed. So just a double check for the simple function, which was a linear function, but the idea basically is that you start with a point and then you can keep moving it to whatever x or y value you want, and nothing really changes. You still have the same finding the derivative, squaring it, and then setting up s as a function of x in this case to find the curve length function.